Hello, today we're going to talk about an introduction to Monte Carlo simulation in GoldSim. This is the January 2024 webinar. All right, so what is Monte Carlo simulation? Monte Carlo simulation is a computational algorithm. This is foundational within GoldSim. It's part of the entire framework. So you'll see as I walk through examples how it is pretty much built into most every aspect within GoldSim. Um, so it is a big part of GoldSim modeling. It's not necessarily something that you have to do in GoldSim, but definitely because it is part of the foundation of it, it works very well within it, and definitely a very important subject when it comes to GoldSim modeling. So um, those of you that have joined, hopefully this will be a productive meeting for presentation for you and helpful for future models that you'll be building. So this is a computational algorithm that allows you to essentially do a lot of repeated random sampling. And what it allows you to do is estimate outcomes that are essentially the outcome of uncertain events, behaviors, processes, inputs, and um, GoldSim provides you a framework to control the or to input model parameters that are controlling the behavior of your system that you're simulating, and these parameters are going to be inherently uncertain. What Monte Carlo does is it allows you to propagate that uncertainty that you've put into the model throughout the model as various functionality takes this input and propagates it through all of the systems within your model. This algorithm was originally developed as part of a nuclear weapons project in Los Alamos in the early 1940s during World War II era, and it was named after a city in Monaco, Monte Carlo, where uh, a lot of chance games occur for um, looking at what is certain outcomes of these types of games. So it kind of makes sense to use that name for simulation as well. So before we dive into how does this work within GoldSim, let's talk a little bit about what it means to set up a Monte Carlo simulation. So first, we need to understand what is uncertainty, and it really just has to do with not knowing, right? It's having doubt about something, about information, a lack of certainty. It means we don't have full knowledge of what an outcome might be or what an input might be. Um, so because of that, it's impossible to know exactly what a future state of your system would be exactly, right? So it's important to incorporate the uncertainty and propagate that through your model so that you can come up with an answer that is representative of possible outcomes. So we need to look at the difference between error and uncertainty. So error is where you have something that you've derived or maybe you've assumed, and that is when you compare it to the true value, not the same, right? Uncertainty represents a range of true possibilities. Uh, so, for example, the climate, um, our, the weather. There's multiple true possibilities that could come about. We just don't know what that is. So there's those two things that we need to consider when developing this kind of model. All right. So what types of uncertainty do we have? We have parameter uncertainty. An example of that might be, for example, maybe you're doing a hydrologic runoff model and you need to calculate maybe like what's a roughness coefficient or what's a um, uh, the CN number, for example, a curve number. All of these kinds of things, they there's a correct answer out there. If we did enough measurements in the field, we could find out what that number is, but we don't have that. So there is a true value there, but we just don't know what it is. There's uncertainty around the parameter. There's also uncertainty about future events. Maybe there's a power outage that could occur. Maybe there's an equipment failure. We don't. It's going to happen, or it could happen. We don't know when. We don't know the frequency necessarily. Um, we might know on average, or maybe we have some historic uh, records, that show approximately when things might fail, but in going forward in the future, we don't know that. So other things that are maybe not necessarily events, but processes like population growth, that's certainly one that we don't we don't know. Um, and then there's model uncertainty. So we build the model to the best of our abilities, but there's still like uncertainty about did we build did we build the model to best represent how the behavior will continue going forward? We don't know for sure. So there's uncertainty around that as well. We try to represent the process the best we can, by modeling it, but there's still uncertainty around that. And a lot of this is time dependent. Um, so that's what we're dealing with when we build a GoldSim model. Usually, we're looking at a simulation that progresses through time, and so time is a huge factor in when certain things start to happen, when a failure occurs. So there's uncertainty throughout any model that we build, and so that's why it's important to consider this in our models. Um, Also, again, about model input. So it's important that we identify the uncertain components within the model. What parts of our model could we have uncertainty around? Um, so does that mean we need to add more components if we don't know about it? Maybe we could simplify it. If we do simplify it, then that would increase the amount of uncertainty around it. Um, so we might have, physically based uh, models, and there's a certain amount of uncertainty around that, and also empirically based. Both of those have some uncertainty around them. But essentially, what we're trying to do is we're trying to get um, all of this uncertainty, all of these parameters, all of the information that is driving our model. We're trying to understand the combined effect of all of these things affecting our model and how they all propagate in throughout the model. This is something that it can be difficult to do, but luckily within GoldSim we have a framework that allows us to essentially incorporate this kind of uncertainty throughout both the behaviors of the model and the parameters that we're inputting. Um, but a question that always comes up is, when we show a model that, okay, here's a result of our model, and it shows this whole wide range of possibilities that could occur. Always the question is, well, how do you validate that? Do you just have to throw random numbers at it? Like, how do you know what these input parameters, the ranges could be? So there's some tools that we have available, and it's important to understand the differences between them, and know where you um, where you might be uh, doing something or putting something into the model that is well defined versus something that is not well defined, and uh, um, uh, make sure that that's communicated to your audience in the model. But so some of the tools we have best fit parametric distributions. So for example, you might have a historic data set that when you analyze it, you can see that there's a range of inputs that might be available. You can do things like parametric distribution, or you can parameterize the distribution, or do that through like a best fit. We have tools for that. You can do that in Excel. You can also do that in Python. The SciPy library within Python allows you to do best fit analysis and come up with uh, um, probability distributions. Those those can then be translated very easily in GoldSim to um, use these distributions as inputs. So by doing a best fit, we're essentially taking the range of what has occurred in the past and fitting it so that we can then say, this is not just a total guess here, but we are basing it on, we're kind of ground truthing it on, what has historically happened or what could happen. The nice thing about doing a best fit, instead of just taking exactly what happened in the past, by doing a best fit, you actually um, provide a smooth uh, probability distribution that includes the tails of the probability distribution, which allows you to look at maybe something that hasn't necessarily occurred in the past. It has a very low probability, but that is uh, likely or probable that eventually something like that could occur in the future. Um, you can also do user defined. You can define a probability distribution that is user defined, non-parametric, meaning that it just simply looks at the data that you give it, and instead of just fitting a distribution. We'll talk more about that as I show you examples. That there's also something else that needs to be incorporated usually in these kind of models, and that is subjective assessments and judgment calls. So sometimes you just have to use your knowledge about these kinds of systems to come up with a range. So, for example, maybe you're looking at what is the seepage rate within some depth of within the ground somewhere when rain is falling, and you want to estimate what is the rate of seepage there. Using uh, your background and your knowledge about these kinds of systems, you could, and maybe with some limited investigation, you would at least know what are what is possible and what is impossible, and therefore you could couch that within a range of possibilities in your model instead of putting in something that is completely impossible. Um, According to your judgment as an expert in the field. It might require reaching out to others that have expertise in certain areas. But using these three tools can provide you what you need to validate your uncertainty. And it is an important step. It is something that will give your model more credibility and ability to defend your model going forward, because honestly, uh, um, there are a lot of people that uh, don't trust. They lose trust in a model if they see that that a model is not producing a single output instead of a range of possibilities. That makes a lot of people uncomfortable, but it is something that needs to be looked at. It's impossible to say that in the future we have one possible outcome, right? And it does give showing one possible outcome does tend to give people a higher comfort level initially, but it also should make people question, how can you say that there's one possible outcome in the future, right? So it's really important to consider this when building any model that is simulating any kind of future scenario. So back to quantifying uncertainty. Within the GoldSim framework, we have, and these are screen captures from within GoldSim in our documentation, showing that we have a long list of possible distributions to select from. The one that's chosen here, you can see it says normal distribution. We have a whole long list of them. Um, you can also define your own custom distributions if you need to, but essentially a probability distribution that one of these you have to pick from is essentially a representation. It's a numerical or mathematical representation of the likelihood of uncertain variable having a specific value. And there are different ways of viewing these probability distributions. And there's different kinds of probability distributions. So normal distribution, is the very common commonly known shape of this kind of bell curve with the tails, where the height of the probability distribution, and when you're looking at the probability density, it's going to show you where it's most likely. So in a normal distribution, it's most likely going to be a value that's centered at the highest point on that curve. The least likely would be those low points, the tails on the ends. You might have a uniform distribution where it's equally likely throughout. There's other distributions, simple ones like the triangular distribution, where it's very simple to define that. Other ones are more complicated, but there's a lot of different types, and it would be good to, in your case, understand these different types, understand how would we, fit our data set or our knowledge of our uncertainty for an input to one of these distributions. Okay, there's different ways of viewing them within GoldSim. It's kind of important to understand these different views. So the common one that I was just showing you is probability density function. That's the first one shown in the top right, and this is the one that shows you probability density. The next one is cumulative distribution function, which is cumulative going from left to right as you look at any point on the graph there. So for example, going closer and closer to the right side, then what you'll see is that it's the probability of that value being less than that number. And then you can swap it and go the other direction where it's the probability of that value being greater than. That's the cumulative complementary cumulative distribution function. So those are the different views. They're all the same distribution, but it's just different ways of looking at it. Okay, so within GoldSim, when you perform a Monte Carlo simulation, what you're doing is you're sampling a value from the probability distribution, right? The most simple case being a uniform distribution where every value is just as likely as another that you might sample. It's essentially just a way to pick a random number, right? And so a normal distribution, when you sample a value from it, most likely it's going to pick something from the highest point on that, but it could be anywhere within that distribution. When I say sample the distribution, what I mean is that GoldSim is going over to that distribution and saying, I want a random number, and I'm going to pick a number from that probability distribution, right? And normal distribution meaning most likely in the middle, in the center of it. And when it picks that value, then it will perform a simulation as if it's a deterministic simulation once it's picked that value and move forward. Now, it doesn't, you might pick a value one time, you might pick a value or sample a value from it multiple times through time, but either way, the model will automatically pick a random value from it and continue going forward through time, and essentially simulating as if that was a deterministic simulation and produce one possible outcome. And that would be representative in this image below as one of those lines. Then it repeats and it does another sample from that distribution, performs a simulation, and produces a separate line, totally independent of the first one. And then it repeats that process automatically over and over for the number of realizations that you specify that you want it to run. And then GoldSim will automatically aggregate those results for you to show you things like probability of a certain type of time history outcome, for example. So this is essentially a similar way to look at it on the right, this repeating process that GoldSim will go through. Essentially, you have these system parameters that have uncertainty in them. Those are then driving equations in your model, and it simulates the system. You might have, in addition to your parameters, you have random events that might be occurring during the simulation. And also, by the way, your system parameters may not be static, right? Your system parameters might be a time series, or um, maybe a table of values, or it might be um, a value that's resampled through time. Right? So essentially, your dynamic system is taking these uncertain values as it walks through time, as they're different, and random events, and propagating those through all of your equations until you get to the end where you have some results that then it stores those and starts over again and does another simulation. So let's say you have a 100-year simulation. It will go through the 100 years with all of this randomness, save those results, start again, do it again for 100 years, do it over and over, and then you'll end up with as many realizations as you specify, as many simulations, that it then takes all of those results and provides you with outputs that's a combination of all of these independent simulations that it performed multiple times. Okay, so the result of this kind of modeling is we can do things like calculate risk. Definitely a very important outcome of a model for a lot of reasons. But this is essentially predicting the probability of some sort of outcome. Usually it's a bad one, right? Risk usually has a connotation of something that is bad, right? Maybe you want to know what is the chance of our reservoir getting too full and spilling, and we end up discharging when we're not supposed to, and we get a fine for that. What's the risk of that? What's the cost associated? We can calculate that going forward. Reliability. Maybe we have maybe some redundancies built into our system to prevent a failure, but there's still a chance, right? There still could be a chance of a failure. How reliable is our system? Can we repair things fast enough? Can we come back and maintain it so that it doesn't fail again? What does that do to increase our design life of our system? So reliability is a way to uh, prevent or reduce risks. How reliable is our system? Can we increase the reliability to decrease our risk? Okay, so with that, I didn't want to spend too much time on all the background. You can learn more about Monte Carlo simulation, probabilistic simulation in GoldSim if you go to our online course. We also have model examples and just our documentation that comes with GoldSim. All of these things describe from multiple angles how to first work with uncertain information, how to propagate that through your model, and then also how to analyze the results of such a simulation. All of these things are well documented within our help system and our online course and model examples. And I do encourage at any point you to ask questions and let me know if you need clarification or need help looking for where you might find help or online documentation about this subject. All right, so with that, let's go into some examples. Okay, so now we're looking at a blank GoldSim model. I'm going to open some examples here. So the first thing I want to do is I just want to talk about, just from the most basic standpoint, just starting from scratch. Let's talk about first of all, how do we set up a Monte Carlo simulation in GoldSim? The first thing I want to do is talk about working in the simulation settings, because that's really kind of where we start to set up the framework. But before you go there and say, oh, I want to run a Monte Carlo simulation of my model, it's really important to first have your model working under the simple, a simple case. When you start running a Monte Carlo simulation, you're dealing with a lot of information. And so it's a good idea to save the Monte Carlo simulations to the end after you've built a model that you can rely on, that you understand, and that has been tested and validated. And then once once you feel good about the model and are ready to move forward, then is a good time to move into Monte Carlo simulation. However, you can start from the ground up, looking at uncertainty and running Monte Carlo simulations as well. So if I go here to the simulation settings, what we have here is a very just a default model that's set up with an elapsed time basis, and it's running for 100 days, and it has a 1-day time step. Already, before we even begin here, we've already got a lot of things going on. We've got 101 scheduled update times, so that's 101 values that we will see if we look at a time history. Before we go to that point, I'm just going to start with a static model, because I just want to show how we come up with uncertain inputs without walking through time yet. Okay, with the static model, now we only have one scheduled update time. That means one output will be produced for example, for one expression, and we don't propagate through time yet. In the simulation settings, you can also see that there's this Monte Carlo tab, which we will be going to. For now, I will just do one realization. So I'm checking this box to select one realization. We will be running a single realization or a single simulation for 0 time. So that's just doing one calculation. All right, so let's take a look under that condition what we get if we put in a stochastic element. So just to review, the stochastic element is inputted here from the inputs category of our element library, and then I select stochastic, and it puts this element in here. So here's the stochastic element. This allows us to pick a random number. So how do we pick a random number? Well, we need to, like all elements, obviously put in the ID description, display units, those are all important. This is a scalar, meaning it only will output one value. Instead of a range, instead of a table of values, a vector of values, it's only one value. Down here in the distribution section, this is where we define the probability distribution and also how many times or how often we will go and pick a random number. How do we trigger going and picking a random number from the stochastic? Somebody asked, will GoldSim sample close to the 50th percentile if you only run the first realization of a multi-realization setup? That is a really good question. No, it will not. It will actually be random somewhere on the distribution. However, you'd see down here in the stochastic, already down here we have something, and this is, by the way, when you first put in a stochastic, by default, it looks like this. It's much simpler than what I have in my first stochastic element. But if you click on the more, you see there's all these other possibilities. So that's what's happening over in this stochastic element. We clicked on the more, and there's some more things that I'll go into in a bit. But one thing I do want to say in answer to your question is, what do we do if we decide not to run a Monte Carlo simulation? We just want to run a deterministic simulation where we don't put in randomness in the model. Well, we have to tell it what to do with the stochastic if we decide to go that route. And you have options here. We could say, well, if we decide to run just a deterministic simulation, let's just go ahead and just grab the mean value. And so in that case, if we did not run a Monte Carlo simulation, then this output would be the mean. So you can control that, but that only happens if you do a deterministic simulation. So if I go back to the simulation settings, and then I go to the Monte Carlo tab, that would only happen if I checked this option down here, deterministic simulation. And there are some global options too here. So we could say, if I have a deterministic simulation, then I just want to use mean values for everything. Then you would select this one. Or I want to use whatever I've selected at all the elements. So you've got some flexibility there. Also 50th percentile. I think that's actually what you asked, is 50th percentile. So you might check this one. But we are doing fully probabilistic right now. Okay, so what that means is that we will pick a random number. And there's one thing And we use Latin hypercube sampling, by the way, and you can look that up in our help documentation or Google that if you want. But this third checkbox down is really important, and this is the default and probably the way you want to keep it most of the time. But it says repeat sampling sequences. So what that means is that yes, it's going to pick random numbers, but every time you rerun the model, it's going to repeat those same random values, those same random locations that it sampled in the distributions will be used every time. The reason for that is because when you're debugging a model and rerunning it, you want to make sure that you understand that uh, uh, it's it's going to be working the same way it did before. Uh, Otherwise, it's going to be picking something random from the previous run every single time, and it's more like that would be more like maybe like a game that you're playing, or maybe like actually rolling the dice every time. You don't know what it's going to pick. That does actually make it harder to build your model and rerun it and make sure that it's valid. So it's important to make sure you understand the difference between this being checked and unchecked. So currently, since our model is set up to be probabilistic, that means when I sample a value from this stochastic, meaning this, when I pick a value from this normal distribution, it's going to pick a value that's random from it, not the mean or the 50th percentile. Somebody asked, how do you determine the number of realizations to run? Okay, that's a good question. I'm going to try to save that for later, but essentially, it has to do with how important it is for you to look at the extremes. That would be one way to look at it. So, for example, maybe you wanted to say, I want to look at the 1 percentile, right, of possibilities. Well, you don't really have a good idea of the 1 percentile unless you have at least. Now, I would need to verify this with a statistician, but you would need at least, I think, 200 samples or more, something like that. Um, you can't get the 99 percentile, the 1 percentile with only, with less than 100 samples, right? So you would need enough realizations to essentially capture those lower probability outcomes there. So yeah, sample size is based on the number of realizations, and you need to have enough of a high enough population of those samples in order to calculate some of those more extreme probabilities. I hope that answers your question. Um, okay, so in this stochastic element, I'm clicking on this edit button here under the distribution. You can see right now it says type normal. If I click edit, you'll see here's a normal distribution. The default, by the way, is always going to be uniform, which looks like this. Uniform between 0 and 1. If I go back to normal, it just kept the same mean and standard. It kept the same value 0 to 1, but now it's the mean is 0 and the standard deviation is 1. That's a totally different just probability distribution that looks like this. So what this means is the mean is 0, right? And it has a standard deviation of 1. So then the tails come out here. And you can actually use this little calculator down here to say, what's the probability of getting a value of 2? You can see that and this is a cumulative probability, by the way. So cumulative probability would be associated with this type of a view. It's the same probability distribution, but it's a different view. So this is the cumulative probability. And looking at this cumulative probability, if I pick a value of 2, that's right about here where I'm pointing. So this is the probability of a value less than 2 being chosen. And that's a pretty high probability, 97% chance that you have a value less than 2. That's what this is saying right here. So then we could say, what's the probability of getting a 1? You can see it's 84% chance of having a value of 1 or less right there. Okay, so with that being our probability distribution, a normal probability, And you can see if I hover over it, it also shows you what we have: mean of 0, standard deviation of 1. Now we need to tell it how often do we need to resample this probability distribution. For starters, let's just go with sampled once, like that. So it's sampled one time, and it's going to pick a random number. All right, so that's pretty simple. Let's go ahead and run the model. The model has completed, and I don't have any time histories because this is a model that has run for only 0 days, so it's static, but we can look at its value. The easiest way is just to hover over it, and you can see here it picked a value of negative 0.48. If I rerun the model, what did it pick? Same thing. So that's what I was talking about with the resampling. If I come up here to the Monte Carlo tab and I uncheck this box that says resample or repeat sampling, and then if I run the model again, you can see now it's a totally different number. Run it again, totally different number. Okay, so especially when you're building a model and working on it and trying to make sense of it, it's a good idea to check the box for repeat sampling sequences. Okay, so now let's go ahead and add, let's just start running multiple realizations. So to do that, I go back to the simulation settings, click on the Monte Carlo tab, and uncheck this box for running the following realization only. And I'm going to run 100 realizations now. I click OK. And also, when I run this, I want to see what's called a distribution result. And that is an element we have right here in our results called distribution result. And I want to link this, I want to connect the output of this stochastic to this distribution result. I don't have to do this, but because I could just right click on this element and find that distribution result. But I want to have a formatted chart, that I can show my audience that stays, that persists in my model and save it. So I'll go to the properties of this distribution result and I'll just link the stochastic here. So just FYI to do that, add result, link to the stochastic, like that. Okay. All right, so we have that linked, and now we run the model. And down at the bottom of the simulation window, or the model window down here in the status bar, you see it shows 100 realizations have been run. If I double click on this chart, then you see here's the PDF view of the results. Okay, so this is a different kind of view, right, than what we saw in the setup of this stochastic element. Let's open both, kind of compare them. So on the left we have essentially a smooth, curved, fitted probability distribution, a parameterized distribution. It can be defined using an algorithm or using an equation, right, to calculate this curve. That's different than what we have on the right. Even though if we look at, for example, some of the statistics of this distribution, we get fairly close values. So we can come over here. I can't actually work with this yet because I have this window open, which is blocking working with that. But we could look at some things over here in this calculator. We could say, well, what about the probability? Let's say probability is 0.01. And it says here that that's a value of negative 2.3. So that's right about where I'm pointing right here on the curve, right? 0.01. If we come over here to the result, you can see 0.01 refers to this value, negative 2.48. So it's a little different here. Why is it different? Why are we not getting exactly the same value? This is a question we see from people from time to time. The reason for the difference is over here on the right, we're just sampling a few numbers. In our case, 100 values. This is not based on an equation here. This is based on sampled values, and it's just showing you the values that it has selected. In fact, if I close this, now we can look at, now knowing that, let's look at the values that it actually picked. So here are all the numbers, 1 through 100. These are all the outputs for 100 realizations this model has chosen. And we could sort it if we wanted to. We could look at what's the smallest number, negative 1.75, all the way up to 2.6. So yeah, it's picked quite a few numbers, but these probabilities and these resulting values are not as accurate as what you might see in the parameterized fitted probability distribution. Well, that's because we've only run 100 realizations. So what happens if we run more realizations? So let's take a look at that. So I'll go back to the simulation settings, Monte Carlo tab, and I'll change this to 1,000, so quite a bit more. Run this again and open up the result. And now look at the curve. Now it's getting closer to what looks like a smooth normal distribution. Compare that to this. So now when we look at the 0.01, come over here, 0.01, this says negative 2.3, this says negative 2.3. So we're getting closer. And so this is an answer to that first question. How many realizations should I run? Well, if it's really important for you to see the 1 percentile or smaller or greater, 99 percentile, then you're going to want enough of a population to be able to more accurately calculate those kinds of percentiles. Okay, so we've done this for just one time step, essentially. This is a static model, right? There's no propagation of time in this simulation. So that's where things start to get a little bit more interesting. Let's go ahead and start doing that. Going back to the simulation settings, first thing I'm going to do is change this back to 100. I don't need that many realizations. Also, for now, just to keep things basic, I'm going to change this back to running only a single realization. And then going to the time tab, I'll change this to an elapsed time model that runs for, let's say 50 days. And then I'll give it a 1-day time step. So that's 50 values. Now we're walking through time, right? We're not running multiple realizations here. We're just going to run a single realization. It will incorporate uncertainty, but we're only running a single realization. And we're going to run it for 50 days. Also, in my stochastic, it's important to understand how many times do we sample a random value from the stochastic. In this case, 1 time for the entire realization. Okay, so when we do that, I run this model. Now I want to look at a time history. So this is a different kind of output, right? This is a time history output. And if I go to the properties of this thing, you can see it's linked again to the stochastic here. Okay, so when I double click on it, then we can see that it picked a random number. In this case, it picked negative 0.48, and it held it constant through time. That's one possible way of incorporating uncertainty into your model. You might have a value that is a constant in your model. A good example is the curve number for a watershed runoff model, right? That's a constant, or yeah, most likely constant, or roughness coefficient, something like that. Those are constants, and we just don't know what it is. So this would be a good example of when you would have this type of stochastic element in your model that you only sample 1 time. But it's important to note that if you run it for multiple realizations, it's going to pick a random number on each realization. So let's see what that looks like. So I go back here to the simulation settings. I uncheck this box for 1 realization. So we're going to run for 100. Now, when you do that, by the way, it's always going to pop up this message. And it always does this because it wants you to know that, hey, usually when you do a single realization run or deterministic, usually you can, when you run the model, you can right click on any element or any element that has results and see the history. Well, we don't want to do that for Monte Carlo. There's just way too many results to save, right? So we turn that off. We turn that ability off. However, the results are saved in your time history result elements. That's where the results are going to be saved. We just do that to try to conserve memory storage requirements. It's just too much information to be able to have to save multi-realization time history results in every single element. That's just too much. So when we change to a multi-realization simulation, it's going to show you this message the first time. Okay, so now we run it, and it's complete. It ran for 100 realizations for 50 days. Now I look at the history, and by default, it's showing me just a single realization. It turns out it's the last realization of 100, but we can flip through this, and you can see it's kind of bouncing around. We can also look at all the realizations, and interestingly, you'll see that there's kind of something going on here. There's fewer values chosen on the extremes, and that corresponds well with the probability distribution PDF view here, where the highest point is where the most likely values are. That corresponds to what we see over here, where we've got more and more lines toward the center. So this is almost, this PDF view is like a cross section essentially. It's taking a cross section of this history. It turns out this probability distribution here, the distribution result, this is showing you the final value right here. So that would be like taking a cross section over here on this right side. Okay. Oh yeah, and then of course another view is the probabilities view. So this is showing you shaded sections of the time history that correspond to the probability values or the percentiles pairs, where this is the 99 percentile and this is the 1 percentile. Or sorry, 99 is up here, 1 percentile is down here. Okay, so those are the different views we get when we run multiple realizations. Okay, so that's a constant. Now we were dealing with a constant stochastic. Now let's look at one that's resampled through time. So if I choose resample, then I click on this resample trigger definition. And now what I can do is I can say, hey, you know what? I don't want to just pick one value in time. I want to sample from this distribution again and again through time. And I want to do it every day. I have 50 days in my simulation. I want to pick a new number every single day. So I'm going to select a different type of trigger called onChanged, and then put in here a run property that refers to the day of the simulation. A good way to do that in a duration type simulation like this is eDay. And this is a run property in GoldSim. Let's just quickly review that. Come over here to the browser, right click, show element subitems, and you can see local properties here. eDay is right here in the elapsed time category here. So this is a built-in property of GoldSim. If you refer to eDay, it's going to be a counter that starts at 0 in this model, and then as the days progress, it just counts by integers, 1, 2, 3, etc. Now that we're resampling this every single day, now what we will see when we run this model is randomness through time. Here's a single realization, and I can walk through the realizations. You can see they're all random, and then all the realizations look like this, probabilities look like this. Okay, so now what we can do in addition to that is we can put in correlation. Oftentimes you have a stochastic that is correlated to another stochastic. So I could put in another stochastic over here, stochastic 2, and I could say this one is looking at, I don't know, let's just say an exponential distribution that looks like this, but it's correlated to stochastic 1. So then we come down here to more, select correlated to, and then put in the name of the other element and say it has a correlation, let's say a value of 0.9. You can put a number here between -1 and 1. A value of 1 would be perfectly correlated, meaning in the first stochastic, if we sample the 50th percentile, then down here in this stochastic 2, we will also pick 50th percentile when we sample it. But if we put 0.9, it's going to be close, but not quite the same. So that's a way to correlate the two. In addition to correlating two stochastics, we can autocorrelate through time, meaning the value that was the sampled, where we sampled the 50th percentile on the previous time step, the next time step, we will pick a value close to that if we provide an autocorrelation value close to 1. So I'm going to do autocorrelated. This is correlated through time on the previous time step. I'm going to say 0.9 here and then run it. This is a good way to incorporate memory within the system. It's common that you have memory in the system that's like an environmental system where maybe you have a runoff, a climate, any hydrologic systems, those often have memory involved in them. And so now when we look at this, if single realization, you can see that it's not just totally random from one day to the next. It's actually, if it's picking high today, then tomorrow it might also pick high. It's not just going to be totally going up and down randomly. And so this is a good way to look at a propagation of information that might be kind of dependent on what it picked the day before, or days before. Okay, so now that you understand kind of how to view results, how to input some stochastic, let's look at some more detailed examples. Okay, so this model is a dam break model. The algorithm is based on what you would find in a tool called HEC-RAS, built by U.S. Army Corps of Engineers. These equations are similar, and what we have is a bunch of stochastics here that represent the breach parameters. So we're talking about a dam break here, an earthen dam break, and there have been observations made of dams that already broke, and they were analyzed, and they looked at things like what was the final bottom breach width. They estimated how much time did it take to breach, all those kind of things. So those are inputs, but they are correlated, and it even shows in the literature, like in the observations, how these things are correlated. So you can mimic that kind of correlation of inputs, and that's what's being done here. So for example, this input here is the time to total failure in minutes. So we have a time to total failure with a distribution like this, and then it turns out that the final bottom width of the breach, according to observations, is loosely correlated to the time of the total breach. So, and it's an inverse correlation in this case. So we have a negative value here in our correlation, but that has an impact, definitely has an impact on the possibilities going forward of what we could see. So for example, if historically, if we analyze a bunch of these events and we see that there is this inverse correlation, then it turns out that you wouldn't have a positive correlation here. You would have most likely a negative correlation. So you wouldn't want to analyze a bunch of realizations where it's a positive correlation, because you don't see that in the history, right? You don't see that in the observations. So we want to use our judgment, and we also want to use whatever historic records that we have in order to make an informed decision about what we put in our inputs like this. It turns out that by doing these things, we can then look at other correlations on the output side. So in this case, we can look at things like, well, how does the breach width correspond to the peak flow of a peak hydrograph, where the flow is, when the flow flows through this breach? What is the peak flow? And we can calculate that using hydraulics and determine what a peak flow is, and then we can correlate that peak flow value to the breach width inputs. And we do that by running the model. So this model runs for 120 minutes, very short duration, very small time step, and we can see what our hydrograph looks like. So here's what the hydrograph looks like after running for 200 realizations. We can look at a single hydrograph. It turns out this is a water level and flow hydrograph on one chart here. So when you look at a single realization, you have the ability to put a Y1 and Y2 axis, but when you look at things like probabilities, it only can show one axis, right? So we can't show multiple outputs, only one output in this case. It's too complicated to show multiple outputs. So just keep that in mind. But then we can come over here and we can choose, okay, do I want to look at water level over time, or do I want to look at the hydrograph? But here's another type of chart that I didn't mention yet, and that's a multivariate chart. So when I open this one, now we can see how does one input correspond to one of the outputs. In this case, on the y-axis is the output of the peak flow versus the breach width, and we can see that there's a correlation. And then you could compare this to, if in the literature there's observed, uh, there's observations of this type of phenomenon. You can compare that, and it gives you a sense of validation for a model like this. Okay, so this is one model. Unfortunately, we don't have a lot of time to go really in depth in these. I just want to give you a basic idea of some of the things you can do. Here's a model where we're looking at reliability of a water supply, and it's very simple. But I just want to show you just kind of basically what's going on here. We have a pool element that's representing a reservoir that supplies water to whatever water supply, whatever demand we have for water from this supply. There's an uncontrolled inflow coming in. It's just whatever it is. I'm using a stochastic element to define this inflow that comes in. It has a capacity. It can only hold so much, so there's some overflow that might occur. But then as we walk through time, we're going to pump water from this pool and deliver it to our water supply. So we have this demand that's kind of independent of our inflow over here, and we're using the pool to regulate and be able to supply as much water as we can. But sometimes we're not able to provide all the water that's needed. So in order to evaluate that simplistically, I'm going to run just a single realization just to make sure I can understand what's going on, right? So I'll run just a single realization, and then I'll look at this time history of how the reservoir is operated over time. So this is a single possibility, one possibility out there. What we have here is the black line is the pool volume on the Y2 axis. You can see it's down low here, and then it rises quickly. It hits the top maximum capacity and overflows. This green line is overflow, spilling. And then these are kind of thin lines. I should probably make them a little thicker, but this blue line is the water demand, and the red line is the water supply. I'm gonna make that a little thicker. So down here at the bottom, you can see the water supply. It's being supplied except for over here at the beginning when the water level was low, so it didn't supply some water right there. So let's see what happens when we run this model a lot of times, a lot of realizations. Let's say 100. Run it for 100 realizations. Okay, running the model. And now we can walk through time, and we can see that there are times when we have multiple shortages occurring. And that's because the water level dropped down low enough that we had to shut off the water supply. It turns out we have a method in here that's telling it to shut off once we drop below this. There's this gray line. I don't know if you can see that very well. There's this gray line. It's kind of our dead band zone, or we could call it our conservation water level or something like that. But essentially, when we drop below that far enough, we're going to say, okay, we're too low. Let's shut everything off. And that's what happens here. And then we turn it back on when we've recovered from this kind of drought period, you could say. So the combination of all of that is complicated, right? I mean, there's a lot of things going on here, but the nice thing is we can essentially use some GoldSim elements to kind of tease out what is going on here. For example, how reliable is our system? What's the risk of not meeting our supply? So with a dashboard, we can do things like this. We could say, okay, let's assume that a significant shortage is defined as a certain amount of volume of water that's not met. Let's just say 600. I just said it in here. This is totally random, but I said if we have a shortage of more than 600 megaliters, I know that's a lot, but if we have a shortage of more than that, that's considered a significant shortage. What is the chance of having that much shortage? Turns out it's 17%. Well, how did I get that? How did I get that number? First of all, we need to do some calculations. So let me just show you that. I have a supply shortages container in here. All I do is I say, I need to know what the shortfall is. I need to integrate that over time because I'm trying to figure out, do we integrate more? Do we have more than 600 megaliters shortage? The only way to know that is to calculate a shortage over time. So I do that with an integrator and I say, here's my water demand less the supply. coming out of the reservoir, that's my shortage over time. So that's pretty simple. We integrate that, and then we say, what's our significant shortage? That's 600 megaliters. Then I just say here, is the shortfall that's integrated greater than that? Yes or no, true or false? And this will be one value per realization at the end. That's all we need to know. At the end of each realization, is this a yes or a no? And by doing that, then we can just link this output, which is just a Boolean, true or false. At the end of each realization, that will have a value. So if I run this for 100 realizations, there's 100 Boolean true or falses that that we come up with. So the nice thing about a dashboard, we can kind of roll up all of that information to calculate things like what's the risk of that. So in a result display, now a result display in a dashboard is just one of the result controls that you can put in a dashboard. So if you click on the properties of this result display, if you change the output display to show display Monte Carlo result, then it allows you to look at statistics of that output, of all the realizations that were run. So we could do something like say, what is the probability that this value is true? That's the same thing as saying 1. If it's 1, that's true, right? If it's 0, it's false. So what's the probability of a value being 1? And that's how we get the value of 17%, 17% chance. We can also look at the mean. So I can look at that integrator that says, what's my shortage? And I can say, oh, I want to know, I want to ask, what's the mean, or what's the 90th percentile, etc. So with that, then we can run the model and we can look at, and this, as it's walking through time, these numbers are changing. But that's how we get that this is our mean shortage. We can also look at the chart of our, that right here, shortage distribution. We can see what is the distribution of our shortages. So on average, it's about, this says not average, there's a mean and then there's a 50th percentile, not the same thing, right? But our 50th percentile is 200. The kind of extreme side, maximum, not maximum, but getting closer to maximum is 1500. So you can see the range there. And we're kind of running out of time. We actually are out of time, but I wanted to show one more example, and actually a couple more, but real quick. Another thing you can do with Monte Carlo simulation and GoldSim is you can sample a historic time series. And I'm just going to briefly just mention this. In a time series, there's an advanced option to enable time shifting. So then what you can do is you can either have it shift randomly through the time series on each realization, or you can tell it where to go in the time series, and that could be a random, like for example, a random year, or you can have it be a sequential year in your time series. This is a very common thing for those of you working in a model that has, where you have a long time series historic record, and you want to randomly sample or sequentially sample that as you walk through multiple scenarios or multiple realizations in your model. And that allows you to look at a wide range of possibilities that is strictly based on your historic record. And so when you open up a time history, then you can look at all the possibilities. There's just so many possibilities in here, but we could just walk through and see all the different possibilities there. Okay, so that you can do that with time series. We also have ways to simulate climate. You can simulate climate stochastically, and this can be done with a model that we have in our library called WGen, and it's a way to simulate random rain, temperature. This is all on a daily basis, by the way. Daily rain totals, daily temperature, min and max, average temperatures, solar radiation. All of those things can be simulated, and they are using WGen. They're based on historic records. So you need a historic daily time series to feed this model in order for it to produce simulated values. So while this is running, this takes a little while to run. It goes for multiple years on a daily time step for 100 realizations. While this is running, that's the conclusion of the presentation. So if any of you have questions, feel free to ask now, and I'm happy to answer. But thank you very much for attending this webinar. I hope it was somewhat useful. I know there was a lot of information I just threw at you, but um, hopefully this makes it a little bit easier for you to approach Monte Carlo simulation in GoldSim going forward in your work. Okay, so the model just finished. I know, so we can look at things like precipitation history. So this is daily precipitation, and I can walk through time, and here's all the precipitation. Now, this is not sampling historic records. The values are the this is based on historic daily precipitation, but this is has never been. These are precipitation time series that have never occurred before, but it is based on history. But that's the nice thing about doing a model like this, is it allows you to simulate scenarios that have never occurred before, and it's a good way to look at possibilities in the future. Also, with a model like WGen, it has monthly, for example, you input things like monthly precipitation averages, things like that. Um, these are things that might be changing with climate change going forward. It's much easier to make adjustments to things like, oh, what's the average total precipitation in April? Well, it's a lot easier to make an adjustment to that number than just taking a historic record of daily time series and try to make adjustments to that, right? So it's a powerful way to start incorporating climate uncertainty in a model. And then we can look at things like period results. So this is in GoldSim, you can look at period histories, like what's the monthly total and the annual total precipitation. So this is looking at the percentiles of monthly total precipitation over time. We can also do that for years. And these are just annual totals of whatever it simulated through time. And you could, in a model that you might be doing, maybe you want to show a trend moving upward or downward. Those are things that could be incorporated in a model like WGen. So instead of just seeing it, on average continuing the same as before, it might be going slightly up or slightly down, and you could then incorporate that in your model and see its impact that way. So anyway, there's a lot more you can do with these models, but I recommend that you go to our website and have a look at our model library, and also our documentation, and especially our free online course. We walk through how to, in a kind of a tutorial way, how to model probabilistic simulations. Somebody asked, can you run probabilistic simulation without stochastic inputs? Yes, it is possible. So when you say without stochastic inputs, I'm assuming that what you're talking about is the actual element called a stochastic. So actually, yeah, this model I just showed you with the time shifting. So this model doesn't have any. Okay, well, this is a stochastic. We don't have to use that one. We could use the sequence. So I could change this to shift year sequence. Whoops. Shift year sequence like that. I could get rid of this element. Okay, so this model has no stochastic element, but what we're doing is we're referring to a local property called realization. And realization is one of our local properties here under the simulation category right here. And this just counts. If I run this model for 100 realization, it just starts on the first realization with a 1, next realization is a 2, etc. So if you imagine it has those integers. If we say, oh, I have an index, I have a starting year of my historic record of 1964. That's the first year on record. if I just add a 1 to that, that puts me into 1965, and then it tells the time series to when we run the model, it goes into 1965 and says that's the year I want to pick. The next realization, it will pick 1966, and so on. So that's a way to introduce some, I guess, variability in your model. There's also, in addition to the stochastic element, there's also an event generator called a timed event. So this would be, and I mentioned early on how we have random events that we might want to simulate. This is a way to simulate random events. Maybe you have uh, a power outage that might occur on some sort of interval that's uncertain, right? And this is a good way to do it. You could say, on average, we have a power outage once a month on average. So 1 per 1 month. On average, this is how often we have a power outage, but it's random through time. So you could say this is power outage. And then what we do is when we run this model, you can look at how many times this event occurs. And it won't occur exactly once a month. It will be sometimes less than once a month and sometimes more than once a month. So that's another way to introduce uncertainty without a stochastic element in GoldSim. I hope that answers your question. Any other questions? And if that wasn't your question, if you just want to ask, like, can I run a probabilistic simulation without having these uncertain parameters? Um, there's you need a way to, I mean, a Monte Carlo simulation by default, I mean, by definition, it has to have um, randomness, right? It has to have uncertainties in it, and so these are the main ways to build any kind of differences between one realization and the next. A realization, keep in mind, a realization is a single simulation of your model that's independent of the next realization. They're independent of each other. They're like individual runs that you're doing. And so you have to, on each realization, you have to have a way to say, oh, I'm going to pick a different thing on the next realization from the first one. And so these ways I showed you, these are the ways to do it. It looks like we don't have any other questions. So I've gone way over time, but thank you very much for joining us. And hopefully you can join us next month. I'll be talking about our AWBM model. Also, I wanted to mention we are having a user conference next September, so I highly encourage you to check out our website. Go on there and check out that user conference. They're always well attended and very informative, useful. We're going to have training. We're going to have presentations made by other users that will be displayed there, and you can also do the same. So it's a great time to network and learn a lot more about GoldSim, where it's going, and what other people are doing. So thanks a lot for joining, and hopefully we will see you next month.